Good afternoon, sir. Good afternoon, classmates. This afternoon, we are in Chapter 4, Subgroups and Normal Subgroups. 4.1 Subgroups. In the previous chapter, we saw that for the groups alternating group of n of composition and symmetric group of n of composition, alternating group of n is a subset of a symmetric group of n symbols. One can think of many examples where the underlying set of one group is a subset of the underlying set of another group. This leads us to the concept of a subgroup. Let G of star be a group and its be a non-empty subset of G. Then its is said to be closed under the binary operation star if A star B is the element of each, for all A and B is the element of each. Suppose each is closed under the binary operation of star. Then, the restriction of star to each times each is a mapping from each times each into each. Thus, the binary operation of star defined on G induces a binary operation on each. We denote this induced binary operation of each by star also. Thus, each by star is a mathematical system. It is also follows that star is as associative as a binary operation on each. In other words, A star of B star C is equals to A star B and star C. For all A and B and C is the elements of each. If each star is a group, if each of star is a group, then we call it a subgroup of G. More formally, we have the following definition. Definition 4.1.1. Let G of star be a group and its be a non-empty subset of G. Then, each of star is called a subset of G of star if each of star is a group. Let each of star be a subgroup of a group G of star. Let identity of each denote the identity of each and E denote the identity of G. Now, identity of each star identity of each is equals to identity of each, which is identity of each star is the identity. Hence, by the cancellation property, identity of each is equals to identity. Thus, the identity elements of G and each are the same. Now, let each is element of each. Let each prime denote the inverse of each in each, and inverse each denote the inverse of each in G. Then each prime is equals to each prime star identity is equals to each prime star of each star inverse of each is equals to each prime star each, and star inverse each is equals to identity star inverse each is equals to inverse each. Thus, the inverse of each in each and the inverse of each in G are the same. Of course, if G of star is a group, then a set of identity of star and G of star are subgroup of G of star. These subgroups are called trivial. Example 4.1.2. Consider the following list of groups. In first group, set of zero, addition operation, and next is integers, addition operation, and the rational addition operation, and the real numbers, and the sign of addition operation, and the complex numbers and the sign of addition operations. And the second group is the set of 1 and the multiplication operation. So the dot is the sign of multiplication operation. And next is in integers except set of 0 is a multiplication operation, and the real numbers except set of 0 in the multiplication operation, and the complex number except set of 0 multiplication operation. So each group is a subgroup of the group listed in its right. So for example, integers and first group is integers operation Addition operation is a subgroup of integers, rational, complex numbers of addition operation. So those are is a subgroup of integers addition operation. And the real numbers, except the set of zero, multiplication operation is a subgroup of complex numbers except set of zero multiplication operation. In theorem 4.1.3, let G be a group and be a non-empty subset of G. Then it is a subgroup of G, F and only F for all A and B is the element of each. Inverse A and B is the element of each. Proof. Suppose each is a subgroup of G. Let A and B is an element of each. Since each is a subgroup, it is a group, and so inverse B is the element of each. Thus, inverse AB is the element of each since each is closer under the binary operation. Conversely, suppose each is a non-empty subset of G, such that A and B is the element of each, implies inverse AB is the element of each. Since each is not equal of empty set, there exists A is the element of each. Therefore, identity is equals to A inverse A is the element of each. In other words, each contains the identity. Now, for all B is the element of each, inverse B is equals to inverse AB is the element of each. Every element of each has an inverse in each. Thus, for all A and B is the element of each. Inverse B is the element of each, and so AB is equals to A inverse B is the element of each. Each is closed under the binary operation from the statement preceding definition 4.1.1. Associativity holds for each. Hence, each is a group, and so each is a subgroup of G. Corollary 4.1.4. Let G be a group and each be a finite non-empty subset of G. Then each is a subgroup of G. F and only F for all A and B is the element of each, and AB element of each. Proof. If each is a subgroup, then for all A and B is the element of each, and AB is the element of each. Conversely, suppose that for all A and B is the element of each, and AB is element of each. So let each element of each, then each and each squared and so on, each to raise to the power of n is the element of each, and so this set is a subset of each. Since each is a finite, all elements of each and each squared and so on for each to the raised power of n cannot be distinct. Thus, there exist integers r and is such that 0 is less than or equal to r and less than is, and r rest and each raised to the power of r is equals to each raised to the power of each. Hence, identity is equals to each raised to the power of each minus r is the element of each. Now, each is minus r is greater than or equal to 1. Thus, identity is equals to each raised to the power of s minus r minus 1 is implies that inverse each is equals to each raised to the power of s minus r minus 1 is the elements of each. Let A and B is the element of each. Then A inverse B is the element of each. And so inverse AB is the element of each by the hypothesis. Thus, by the theorem 4.1.3, each is a subgroup. Theorem 4.1.5. Let G be a group and G, center of the group of G, is equals to set of B is the element of G, such that AB is equals to BE for all A is the element of G. Then, G is the center of group G is a commutative subgroup of G. G is the center of group G is called the center of G. Proof. Since A identity is equals to A is equals to identity of A, for all A is the elements of G. Identity is the element of G, center of the group G, and so Z is the center of the group G is not equals of the empty set. Let A B is the element of G, center of the group G. Then BC is equals to CB for all C is the element of G. From this, it follows that inverse CB is equals to inverse BC for all C is the element of G. And so, inverse B is the element of G, center of the group G. Now, inverse AB, C is equals A inverse B, C is equals to A inverse CB is equals to AC inverse B is equals to CE inverse B is equals to C inverse AB for all C is the element of G. And so, inverse AB is the element of G, the center of group G. Hence, by the theorem 4.1.3, G as the center of the group G is a subgroup of G. That Z, center of the group G, is a commutative follows by the definition of G, center of the group of G. Theorem 4.1.6. Let G be a group and set of right coset of each and E such that A is the element of I. B any non-empty collection of subgroups of G. Then, intersection sets of A is the element of I. Right coset of each and E is a subgroup of G. Proof. Since each right cosets of each and E is a subgroup of identity is the element of right cosets of each and E for all A is the element of I. Hence, identity is an element of intersection subsets E is the element of I, right cosets of each and E, and so intersection of sets E is the element of I, right coset of each and E is not equals of empty set. Let A and B is the element of intersection subsets of A is the element of I, right cosets of each and A. Then, A and B is the element of right cosets of each and A for all A is the element of I. Thus, inverse AB is the element of right cosets of each and A for all A is the element of I. Since each of right cosets of each and A is a subgroup, and so inverse AB is the element of intersection subsets E is the element of I, right cosets of each and A. Consequently, intersection subsets E is the element of I, right cosets of each and E is a subgroup of G by theorem 4.1.3. Thank you. Bye.